In this psychophysical study, we focus on translational shape-changing haptic interfaces and investigate various factors that impact user perception. Compared to more established haptic feedback modalities such as vibration and force, shape change is still an emerging technology with untapped potential. We built a cube-shaped shape-changing device whose top segment can slide horizontally on the bottom segment. The user holds onto the device, touching its left and right faces. Haptic information is conveyed via the direction and magnitude of misalignment. Our first psychophysical experiment followed the method of constant stimuli, in which 10 participants each compared 240 pairs of shape misalignments under 3 different grasp types and 4 different reference positions. Participants were listening to white noise and could not see the device as it was covered by a piece of cloth. A Python GUI informed participants which grasp type to use and allowed them to trigger device movements and give their comparison answers. Using the results, we first investigated how user perception depends on the magnitude of shape change. We found that at larger misplacements, users had significantly better perception sensitivities, which is likely due to the increase of contact shape complexity. Next, we wanted to see how different grasp poses can affect perception. To our surprise, having more fingers in contact with the device under the pinch and power grasp have tendencies of worsening user perception. Some participants reported that they could only focus on one finger at a time, which might explain these counterintuitive results. In terms of translation direction, we did not find a strong bias across participants. Yet, some participants had significantly better perception results in either direction, showing that directional bias can exist, but isn't universal. The second part of experiments focuses on the mapping between the shape-changing device's position and the value it represents. We implemented a paddle game in which participants catch falling balls and get scores based on the catching accuracy. A paddle is controlled by users via the laptop trackpad, while the shape-changing device presents the ball positions to the participant's other hand. After 10 balls, the balls become invisible, and the user is forced to rely only on the shape-changing device to gauge ball positions. We implemented 2 different mapping schemes, a linear function and a non-linear function based on the perception results from the previous experiments. In terms of overall error between the ball's landing position and paddle position, the 2 mapping schemes had similar performances. But if we look at the errors split into 4 screen regions, we can see the potential benefits of the perception-based non-linear mapping scheme. The errors are much more even across the screen, and the maximum error was reduced as well. In conclusion, we have multiple interesting findings. Firstly, having more fingers in contact with the device does not improve perception, but more complex contact shapes on the same finger can. Secondly, shape-changing devices are prone to directional perception bias. And lastly, utilizing perception-based mapping methods can likely be beneficial.